Assalamu alaikum. Bismillahirrahmanirrahim. I welcome you to the 28th lecture for the series of lectures on advanced computer architecture. Today, after a brief review of what we discussed last time, I will give you details about the placement and replacement policies of a cache, the cache write strategy, and some cache performance enhancement methods. Last time, we discussed the impact of changes in the block size on the cache performance. We also discussed the categories based on which a cache is designed. Last time, while talking about the impact of changes in the block size, we considered the miss rate, the miss penalty, and average access time, and the impact on these parameters onto the performance of a cache. Here we found that the large block size reduces the miss rate, but if block size is too big relative to the cache size, then miss rate goes up. And at the same time, the miss penalty will go up as the block size increases. We also discussed that by combining these two parameters, the third parameter, that is the average access time, initially goes down with the increase in the block size, but eventually it starts increasing rapidly again with the increase in the block size when the miss rate starts going up again. Here we discussed the cache organization, where we said that based on the block placement policy, cache organization can be classified as the direct map cache, fully associated map cache, and set associative map cache. We said that the direct map cache is one where each block has only one place it can appear in the cache. However, this particular organization gives rise to the conflict miss, whereas the fully associative mapped cache is one where a block of the main memory can be placed anywhere in the cache, whereas the set associative map memory is one, which allows to place a block in a set of places in the cache. From our discussion on the memory hierarchy, we noticed that a memory hierarchy designer should be concerned about four basic questions. The first question is that where a block can be placed in the upper level memory. This problem is known as the block placement problem. The second consideration is how is a block found if it is in the upper memory or not. This particular problem is referred to as the block identification problem. The third question, which bothers a memory hierarchy designer, is which block should be replaced on a miss. This particular problem is referred to as the block replacement problem, whereas the last one is what happens on a write. That is, if there is a write miss, what write strategy is to be followed. Now I will consider these questions one by one, and we will see how these problems are considered by a designer. For this, let us first of all talk about the block placement policy. Block placement policy differs from the one type of memory mapping to another type of memory mapping. Let us first of all talk about the fully associative mapped memory. This is a class of memory where a block can be placed anywhere in the upper level cache. This you can see from this diagram. Here, the block number 12 from the main memory can be placed in a location corresponding to any of the 12 blocks in the cache. So this means that the placement of a block in case of fully associative memory is very simple and straightforward, and it does not need any consideration. Whereas the placement of a block in the cache for set associative memory is relatively complex. For this, let us have a look onto this diagram. Here you can see that for a set associative map memory, a block can be placed anywhere in a set in upper level memory, or say in the cache. Here, to find the set number in the upper level memory, we have to find the mod of the block number with the number of sets. For example, as you can see over here, we are using a two-way set associative map cache which has 4 sets numbered as set 0, set 1, set 2, and set 3. Here, each set consists of 2 blocks. Therefore, a block number 12 or number 16 of the main memory can go anywhere in set number 0, because the 12 mod 4 results in a value equal to 0. Similarly, 16 mod 4 also results in a value 0. Similarly, if we have to place the block number 14 of the main memory into a two-way set associative memory, then it will go to set number 2, because 14 mod 4 is equal to 2. Now let us consider what happens in case of direct map cache. The direct map cache is also known as one-way associative mapped memory. Here, a block can be placed at only one specific location in the upper level or in the cache. Now this location in the cache can be calculated by taking a mod of the block number with the number of blocks in the cache. Considering our previous example, here you can see that the block number 12 or block number 20 of the main memory can be placed at location 4 in the cache having 8 blocks. This is because 12 mod 8 is equal to 4, where 8 is the number of blocks in the direct map cache. Similarly, 20 mod 8 is also equal to 4. Therefore, both the block number 12 as well as the block number 20 will be placed at only one location, that is the block number 4 in the upper level memory. So with this much information about where a block can be placed in any type of memory, that is either in the fully associative or n-way set associative or the direct map cache, let us see how a block is identified in a cache. A tag is associated with each block frame in the upper level memory, that is in the cache, in order to identify the placement of a block in the cache. The tag gives basically the block address corresponding to the main memory. Here, all possible tags where a block may be placed are checked in parallel, and a valid bit is used to identify whether the block contains correct data or not. However, while identifying a block in the cache, we simply check the tag, and here we need not to check the index number or the block offset in case of n-way set associative or direct map cache. Let us consider an example of block identification for a direct map cache. For this, let us consider lower level memory of 4 gigabyte, which has been divided into blocks of 32-bit each. Now for a 4 gigabyte memory, it requires 32-bit address, whereas let us assume that our cache is of 1K byte, and as a first example, let us consider direct mapped or one-way associative cache, which means there are 32 blocks, and each of the 32 blocks has got 32 bytes. So this shows that in order to place a block in the cache, the cache requires 5 bits for byte identification and 5 bits as index, whereas 22 bits tag is associated with each block. The tag of a block is compared with the corresponding upper 22 bits in order to identify the presence of a block in the cache. Here, note that as the associativity increases, the index value shrinks and the tag expands. This can be explained with the help of this diagram for a two-way set associative cache. Here, let us reconsider our earlier example of 1K byte cache, which is reorganized as a two-way set associative cache. You can see that this arrangement has 16 blocks in each set. Therefore, index field of 4 bits and a tag field of 23 bits is associated with each element of the set. This shows that as the associativity increases, in this example from one-way to two-way associative cache, the index field decreases and the tag field increases. So now let us talk about the block replacement policy. That is, how a block is being replaced. In case of cache miss, a new block needs to be brought in. Now, if the existing block location as defined by the block placement policy is filled, then an existing block has to be removed or fired. Now, this firing is done based on what type of cache mapping is used and what block replacement policy is to be used. So, let us discuss this for the 3 different types of mapping policies which we have already discussed. What are the block replacement policies? Let us consider the direct map cache first. For the direct map cache, the block replacement is very simple, as a block can be placed at only one location. As we mentioned earlier, this location is given by block number mod number of cache blocks. So this means that we do not have a very big choice to replace a block in the cache, because any block which has to be placed in the direct map cache must go at one specific location. Whereas, while considering the other 2 types of mapping, that is the fully associative and set associative memories, there are 3 commonly used schemes which are used for this purpose. These policies for the block replacement are known as the random, the least recently used, and first in, first out. Out of these 3 policies, let us discuss them one by one. The random block replacement policy states that you can select any block randomly to replace it. So in this case, we can say that it is the simplest and easiest possible policy, where the candidates for replacement are selected randomly. The cache designers usually use pseudo-random block numbers, and these pseudo-random numbers are generated to select a particular block to be replaced. It is very simple indeed. The least recently used, which is abbreviated as LRU, this policy states that replace the block either never used or it was used long ago. This policy reduces the chances of throwing out the information that may be needed very soon. Here, the access time and the number of times a block is accessed is recorded, and the block replaced is one that has not been used for a very long time. For example, if the blocks are accessed in a sequence, say block number 0, then 2, then 3, then 0 again, then 4, then 3 again, then 0, then 1, then 8 or 0, then in this particular case, the victim to be replaced is block number 2, because in this sequence, as you can see, that block number 2 was used only at the second place, and after that it was never used. Whereas, no doubt, the block number 0 was used at the first place, but it was also used at the fourth place, and then it was also used at the seventh place, and then very recently it is used in this sequence. Whereas the block number 2 is used long ago, therefore it is the most suitable target to be replaced by a new block. Whereas the third policy, that is the first in, first out, or say the FIFO policy, it states that a block which is placed in first is thrown out first. In order to understand this, let us consider this sequence in which the blocks are accessed. If the sequence is that block number 2, then block number 3, then 4, 5, and then 3 again, and then 4 again, then to replace a block, the block number 2 will be thrown out first because it is the one which was placed in first, and it is the oldest accessed block in the sequence. Therefore, we can say that FIFO can be used as an approximation to the least recently used policy. This is because the least recently used policy can be complicated to calculate which was accessed least. Therefore, the FIFO arrangement is simpler as compared to this one. Now, let us compare the performance of these three replacement policies. For this, let us consider this table which contains the data for 2-way, 4-way, and 8-way set associative caches of different sizes, say of size 16K byte, of 64K byte, and of 256K byte. And let us see what are the values which we can get for least recently used policy and the random replacement policy. Here, note that there is a little difference in the least recently used and random policy. For the largest size cache, that is for 2K byte, for any associativity. For example, for 256K byte cache for a two-way set associativity, the data shows that the least recently used and random replacement policy, they have almost similar performance, that is 1.15% and 1.17%. Whereas for four-way set associative, it is always equal, that is 1.13 for both least recently used as well as for random replacement policy. Whereas similar is the result for eight-way set associative. However, the least recently used policy outperforms the smaller caches, that is the cache of size 64K byte and of 16K byte, which you can see that in case of 16K byte, the performance of least recently used is much better as compared to the random for two-way, four-way, or eight-way set associative. So as the size of the cache decreases, the performance of least recently used policy is better. Now let us talk about the fourth constraint of a cache designer, that is, what happens on write. Basically, we want that for writing purposes, we must not overwrite a cache block unless the main memory is up to date. Moreover, multiple CPUs may have individual caches and IOs may address main memory directly, whereas the memory is accessed for both the read as well as write purposes. The caches may hold instructions or data, whereas the instruction cache accesses are usually the read accesses, and the instruction issue dominates the cache traffics as the writes are typically 10% of the cache access. Furthermore, the data caches are 10% to 20% of the overall memory access for writing purposes, whereas for the remaining time it is read. Now let us discuss how we can optimize the cache performance. As we have already discussed in the beginning, that in order to optimize the performance according to the Amdahl's law, we always make the common case faster. Here, fortunately, in case of memory read or memory write, the common case is the cache read, and fortunately cache read is made fast very easily because we can check the tag as well as perform the data transfer operations in parallel. We know that for the memory read operation, basically the only two steps required are the tag checking followed by the data transfer. But as the tag is available as part of the cache, therefore the tag checking as well as the data transfer is performed in parallel. Hence, this case is very fast case. So this gives very good performance of the cache for the memory read or for the stalls on read, because this stall is for a very small time. Whereas in case of cache write, the cache content modification cannot begin until the tag is checked for address hit. Therefore, the cache write cannot begin in parallel with the tag checking, as in case of cache read. Another complication in case of cache write is that the processor specifies the size of write, which is usually a portion of the block, not the complete block in this particular case. Therefore, the optimization of write needs considerations. Let us consider the write policies which can be used for making the cache write faster and optimize the cache write performance. The write policy distinguishes the cache design. The two commonly used write policies are known as the write back policy and write through policy. The write back policy is one where the information is written only to the block in the cache, and the modified cache block is written in the main memory only when it is replaced. Whereas the write through policy states that the information is written to both the block in the cache and to the block in the lower level main memory. So let us discuss the pros and cons of the write back as well as the write through policies. In case of write back, no write to the lower level for repeated writes to the cache is done. Furthermore, the write back policy reduces the memory bandwidth requirement. Therefore, ultimately, it reduces the memory power requirement. However, in order to use the write back policy, we have to include one bit with each block. This additional bit in each block is known as the dirty bit, and this bit holds the status of the cache block as if it has been modified or not. When cache contents are modified at any block position, then this dirty bit is set and it refers to the cache being dirty. Whereas if the contents are not modified, then the bit is clear and it is referred to as the clean cache. Whereas the write through policy, it simplifies the replacement procedures. The block is always clean here. So unlike the write back strategy, the read miss cannot result in writes to the lower level. Moreover, the write through always combined with the write buffer so that it does not wait for lower level memory to get ready to receive an information or to write an information into it. Similarly, simplifies the data coherency as the next level memory has the most recent copy always available. However, the concept of data coherency, we will discuss this at some later stage. Here let us see that how we can overcome the problem of stalls and minimize the stall time by using a write buffer while using the write-through policy. During the write-through, the CPU must wait for write to complete. Therefore, a write buffer is needed between the cache and the memory to optimize or say to reduce the memory write stalls. A common optimization for write stalls during the write-through is the use of a write buffer. Here you can see it from this diagram that a buffer is introduced in between the processor and the DRAM. This buffer is just a FIFO memory, that is first in, first out memory. Typically, it has got 4 entries. Once the data is written into the write buffer and assuming a cache hit, the CPU is done with the write. The memory controller will then move the write buffer's content to the real memory behind the scene. Here, remember that the DRAM cycle time sets the upper limit on how frequent you can write to the main memory. Moreover, the write buffer works as long as the frequency of store with respect to time is not too high. This means that the store frequency is very, very small as compared to the DRAM write time. That is 1 over DRAM write cycle, which is equal to the write time. Furthermore, if the stores are too close together or the CPU time is so much faster than the DRAM cycle time, then you can end up with an overflow the write buffer and the CPU must stop and wait. Now, a memory system designer's nightmare is when the store frequency with respect to the time approaches 1 over the DRAM write cycle time. That is, we call this situation as the write buffer saturation state. In the write buffer saturation case, it does not matter how big you make the write buffer, the write buffer will still overflow because you are simply feeding the things in it faster than you can empty the buffer. However, in order to overcome this problem, there are 2 different methods which can be used. The first solution to this problem is that you may get rid of this write buffer and replace the write-through cache with the write back cache. The second solution is that you install a second level cache between the write buffer and memory and make this second level cache as the write back cache. This you can see from this block diagram where an L2 cache is placed in between the cache and the DRAM. With this much discussion on to the write strategy, let us talk about the write miss policies. In case of write miss, normally two options are used. These options are known as the write allocate option and no write allocate option. The write allocate option is one where a block is allocated on a write miss followed by the write hit action, whereas the no write allocate policy is one where the write missed do not affect the cache, rather the block is modified only in the lower level memory. That is, the block stays out of the cache in no write allocate until the program tries to read the block, but the blocks that are only written will still be in the cache with the write allocate. Let us discuss this with the help of example and see what is the difference between write allocate and no write allocate. Let us look at our earlier example of 1K direct mapped cache again. Here we assume that a 16-bit write to the memory at a specified location and it causes a cache miss in 1K byte direct map cache that has 32-byte block select. After we write the cache tag into the cache and write the 16-bit data into byte 0 and byte 1, do we have to read the rest of the block, say the byte 2, byte 3, and up to byte 31 from the memory? If we do not read the rest of the block, then it is called write allocate. Otherwise, it is called no write allocate. Let us think if it is really necessary to bring in the rest of the block on the write miss. The answer to this is yes, as the principle of special locality says that we are likely to access them soon. But the type of access we are going to do is likely to be another write. So even if we do read in the data, we may end up overwriting them anyway. So it is a common practice to not read in the rest of the block on a write miss. If you do not bring in the rest of the block, or using a more technical term, that is write not allocate, you better have some way to tell the processor the rest of the block is no longer valid. In order to explain this further, let us consider this example of a fully associative write back cache with cache entries that start empty. Let us consider the following sequence of 5 memory operations and find the number of hits and misses when using no write allocate versus using write allocate. In this example program, here the first 2 write instructions are for writing some data at memory location 100. Then it is followed by a memory read from location 200, and then the last 2 instructions are the memory write instructions for writing data to memory location 200 followed by 100. For no write allocate, the address 100 is not in the cache. That is, its tag is not available in the cache. So the first 2 writes will be resulting in 2 miss operations. Now the next one, the address 200 is also not available in the cache. Therefore, it is a read miss operation. The subsequent write, that is 200, is a hit, whereas the last write, that is write 100, is still a miss. So the no write allocate policy results in 4 miss and 1 hit operation. Now let us see what is the result of write allocate policy. In case of write allocate, the first access of 100 and 200 are the misses. The rest are hits because 100 and 200 are both found in the cache after the first 2 miss operations. Therefore, the net result is that while using write allocate policy, there are 2 misses and 3 hits. So from this we can conclude that either write miss policy can be used with the write through or write back, but normally the write back caches use write allocate because it hopes that the subsequent write to the block will be captured by the cache, whereas the write through caches often use no write allocate policy. The reason is that even if there is a subsequent write to the block, the write must go to the lower level memory. Today, we have been talking about the concerns of a memory hierarchy designer, where we have studied 4 basic concerns, that is the block placement, block identification, block replacement, and write strategy. While talking about the block placement policy, we discussed the case of block placement in case of fully associative, the set associative, and direct map caches. Then, while talking about the block identification, we noticed that in order to identify a block in the cache, we always associate a tag with the block of the memory. However, in addition to including the tag, we also include an additional bit known as the valid bit with the cache. Now this valid bit is initially empty, or say it has got a value equal to 0 when we switch on the system for the first time. And when the first instruction or first data has been placed in the respective cache, the corresponding valid bit is made equal to 1. And whenever the controller has to access the cache, it always checks the valid bit and the tag. If the valid bit is 1 and the required tag is available, only then it records this as a hit operation. Otherwise, it is considered as the miss operation. Then we discussed the block replacement policies. In the block replacement policies, we talked about the policies being used for the direct mapped, the fully associative, and set associative caches. The methods used for fully associative and set associative are random replacement policy, or least recently used replacement policy, or the first in, first out replacement policy. Here we observed that there is a little difference in the least recently used and random replacement policy for the largest cache sizes. However, the least recently used policy outperforms the smaller caches. Followed by this discussion, we talked about the writing strategies. While talking about writing strategies, we noticed that there are two commonly used write strategies for cache, which are referred to as the write back and write through. Then at the end, we talked about the situation when we have to include a write buffer and what happens when the write buffer reaches in saturation. And at the end, we discussed the write miss policies as the write allocate and no write allocate policies. Now today, with this much discussion, I will stop here, and next time we will talk about the performance of a cache in terms of the average access time, the miss penalty and miss rate, and we will discuss different techniques, how we can enhance the overall performance of the cache. Till then, Allah Hafiz. Thank you.